Hello and welcome to your Chapter 2 video lecture where we're going to cover atoms, ions, and molecules. We'll divide this lecture into videos based on the section that we are discussing. So we'll start off with section 2.1 on atomic structure. First, we need to define what matter is. Matter is going to have mass and occupy space, and we have three forms. We have a solid form, such as in bone. We have a liquid form, such as in our blood, and we have a gas form, such as oxygen. And an atom is the smallest particle exhibiting chemical properties of an element. So this is an atom over here, and we could see that we have some subatomic particles here that we're going to talk about in a few slides. There are 92 naturally occurring elements that make up matter, and they're organized into a periodic table of elements, which we see over here. I think it's helpful if you print this out or keep this a photo of this handy, because we will be using this all throughout this week. And here are the most common elements of our human body. You could see that oxygen is a major element within our body and makes up 65% of our body weight. And then we have carbon following in at 18.5%. Following that is hydrogen, the nitrogen, calcium, and phosphorus. And we do have some minor elements within our body as well, such as sulfur, potassium, sodium, chlorine, magnesium, and iron. So now we'll talk about some of those subatomic particles. We have neutrons in here, which are the blue bubbles. This is going to consist of the mass of one atomic mass unit, or AMU, and there's no charge to this. So neutral, you can think neutral. And then our protons are the green bubbles here with the plus sign, and this is going to be the mass of one AMU, and they have a positive charge. And then the electrons, you can notice that they are going to be floating in a cloud around the other subatomic particles. They are 1/1,800th of a mass of a proton or neutron, and they have a negative charge, so that's why the little minus sign is in here, and they're located at varying distance from the nucleus in regions called orbitals. So we're going to talk about orbitals in the coming slides, but you could see they are the black rings here are the orbitals. The first orbital can hold 2 electrons, whereas the other ones after that are going to hold 8 electrons. So let's talk a little bit about our periodic table. We are going to see in our table that we will have a chemical symbol, and this will be unique to each element and will help be identified by the first letter or the first letter plus an additional letter, such as C for carbon, or the example here is He for helium. And then we have the atomic number or proton number, which we can represent by the letter Z, and this consists of the number of protons in an atom or of the element. It's always going to be located above the symbol's name, and the elements are arranged by this I know this is an atomic number, but it should be atomic number within rows. And then on the bottom, we have our average atomic mass. This is going to be the mass of both our protons and neutrons, and it's shown below the element symbol on the table. So in order to calculate some of these things, if we need to find out how many protons within an element, we know we could just use this atomic number. But if we're trying to find out what the neutron number is, then we could take this atomic mass, like you see over here, and we could subtract it by the atomic number. And by that way, we are subtracting the protons and we are left with our neutrons. There's another example here of sodium, or Na, and we could take its atomic mass and subtract it by its atomic number in order to get the number of neutrons. So that would be 12 neutrons. Our atomic number was 11, so we have 11 protons. And then our electronic number is equal to the proton number. So if we wanted to know how many electrons in carbon, we would know that it is 6 electrons. And if we wanted to know how many electrons in sodium, that would be 11. It's always going to be equal to our proton number or the atomic number. And now let's talk about diagramming atomic structures. An atom, like we said, is going to have these shells or these orbitals of the electrons surrounding the nucleus. And each shell is given an energy level. Each of these shells are going to hold a limited number of electron shells. Like we said, that first inner one is going to hold 2 electrons, but then the second one is going to hold up to 8 electrons. And shells close to the nucleus must be filled first. So we can't do like one here and one here and then bounce back and put another one here. These always fill up first and then we go to the next orbital. And we can also have isotopes. These are different atoms of the same element, the same number of protons and electrons, but they have a different number of neutrons. They're identical. They have identical chemical characteristics, but different atomic masses. So we could see this as an example down here, these different isotopes of carbon. We've got carbon-12, in which we have 6 neutrons and 6 protons, 6 electrons. So this is our most prevalent type. But notice here, we keep our protons and electrons the same in these carbon 13 and 14, but we're changing the number of neutrons. In this one, in carbon 13, it is 7, and in carbon 14 is 8. Notice how it's correlating with the atomic mass changing. So if we were to take this atomic mass and subtract 6, then we are left with 8. All right, our chemical stability and octet rule here. We look at our periodic table and it's very organized. It's been organized into columns based on the number of electrons in its outer shell. And this is referred to as a valence shell, meaning if we look at the photos down here, this last shell here is the valence shell. But we have, let's see, 1, 2, 3, 4 orbitals here for calcium. So this last one is still the valence shell. And if we look back at our periodic table, we see in column 1A, we are going to see hydrogen and lithium, sodium and potassium, and all of these are going to have just 1 electron in their valence shell. If we looked at the next column, this second column here, these other elements would have 2 electrons in their valence shell. And then if we go across here, you would see this has 3 in its valence shell, 4, 5, and so forth. So each of these consecutive columns has 1 additional electron in their outer shell. And in our elements, where the columns 7A is going to have full valence shells. So they're not really looking to take on more electrons. This means that they are chemically stable, and examples would be helium, neon, and these are also known as your noble gases. So like we said, these orbitals need to be filled one by one. So if we look at hydrogen here, we only have 1. So we want this orbital shell that's supposed to have 2 electrons in it to be full so that hydrogen is happier. So if we look down here at lithium, we see that that first shell is full. We've got 2 electrons there, but now that valence shell has only 1 electron. This lithium is not happy because this last shell can have up to 8 electrons. So it really wants to probably give away its electrons so that this first orbital is full and it is happy. And fulfilling that is called the octet rule. Another example would be down here for sulfur. We see that that first orbital is full with the 2, the second orbital is full with 8, but now its last shell has 6. So it needs 2 more electrons in order to be happy and fulfill the octet rule.